Hey, so now we're going to discuss the RSA algorithm itself. Now, we left off with two equations. T raised to the p equals x with a modulus of r. We also had x raised to the q equals t with a modulus of r. Now, as you can see, one inputs t, outputs x, the other inputs x, outputs t. But, as you can see, this is modulus arithmetic. It's a lot less simple than simple just input-out, because these are signs of congruency, not necessarily equality. So, essentially, this is going to make a hacker's life a lot more difficult. See, now, the P and the R are part of the public key. That's what everyone has. The Q is part of the private key. So, there are certain things in this equation that hackers will not get that the person who you're sending this message to will, and it essentially amounts to Q. So, let's say you send your friend a message. The message is T. It's encoded in numbers, like, A is 1, B is 2, except you wouldn't do that. So, you send them that message, you encode it, you raise each digit individually to the power of P, and you end up with X to a modulus of R. So, you send your friend the X. Your friend gets the x, raises it to the power of q, and starts working with the modulus to get your t. Now let's say some hacker gets your message. Now what the hacker has is he gets the x that he hacked from you. He'll take a modulus of r from the public key and a p from the public key, but he won't get the q, because that's the private key. He doesn't have that. He has no way to get that. You didn't send that. So what he has to do is essentially take these two equations, along with another one that we just know for fact, which is p times q equals 1 with a modulus of phi r. Now, what we're going to do with this is we need to isolate q. So we take the p away from this side and divide it onto this one. Now notice that on this side, what he's essentially going to have to do is, there are a couple of unknowns here. So, we have modulus of phi r, but we can really replace that modulus to make this easier with us. We can make that plus k phi r. So now, once the hacker has figured out what the value of phi r is, he already knows what the value of p is. So he's essentially going to test out values for k until q ends up as an integer. So once q is an integer, he's going to test those values out on the equation that will give you back the value of t. Now, once he comes up with something that is not gibberish, he'll check to see if it makes sense as the message. So that's how you would hack it. There's a reason that he's not really going to be able to get away with that in practicality. Notice that phi r is here. Now, he's not just going to magically get that. R's are not usually small and tame, like the number 55, where you know that it's just 5 times 11, of course. You can do that rather easily. Nor is it actually going to be something so simple as a 6-digit number. It's like child's play. It's going to be something like 100 digits. These are far more difficult to factor. So, if we have like 100-digit r, the issue is that you're really multiplying two numbers together. That's really easy. But for your hacker, he's going to have to start dividing it by 2, and then by 3, and then by 5, and then by 7, and it's going to get painful by the end, and he's really not going to be able to do it very quickly. Not nearly as quickly as he will be able to encode the number. And this is why RSA works. It's because you cannot figure out numbers by dividing it in this brute force search as easily as you can create them simply by making your R a little bit larger. Thank you.